Today's lessons is CSEC Industrial Education, and I am Fitzroy Hibbert. Today we'll be looking at electrical transformers. So, we go right into our lesson. Transformers. Our objectives for today's lesson are, at the end of our lesson, students will be able to define a transformer, state the principles of operations of a transformer, state the relationship between the input and output voltage and current of a transformer, calculate the voltage, current, turns and efficiency of a transformer, calculate the voltage regulation of a transformer. You'll ask, what is a transformer? And chances are a student who is learning this for the first time would say transformer is a movie that comes on TV. Yes, you're right, that's a transformer. But if we're looking at electrical technology, what is a transformer? And the definition for a transformer is an electrical device that transfers energy from one circuit to another by magnetic coupling without requiring relative motion. That means you might hear a little bit of movements here and there, but between its parts. It's a static electromagnetic device that is capable of transforming or changing the value of alternating current and voltage at a constant frequency. I happen to put this in different color. And the reason for this is, a lot of times students might just say, a transformer is a device that step up or step down voltage, change the value of voltage. But you have two kinds of current, what is called alternating current and what is called direct current. A transformer does not deal with direct current to change the value. So I actually ensure that students will realize that we're dealing with alternating current and voltage. So do not leave out the current part of it. Don't say a transformer is a device that changes the value of voltage, full stop. And remember, it says at a constant frequency. What does that mean? At a constant frequency, it means that whatever frequency the transformer is connected to, that's the same frequency you will be getting out. Moving on. How is it constructed? A transformer is constructed with two or more coupling windings, or we say coils. And in most cases, a magnetic core. The coil are namely the primary coil and the secondary coil. So we have two coils. One is called the primary and one is called the secondary coil. They are so constructed on what is called a magnetic core so that the magnetism that is created by one coil is transferred to the other coil effectively without any form of hindrance. Moving on. Graphic symbol and basic diagram. So we look at the graphic symbol for a transformer. This is what you draw if you're asked to draw a graphic symbol to represent a transformer. However, if you're drawing this symbol in a circuit diagram, bear in mind when you come to the board, this would be your symbol. For your transformer, you would label it to say primary and you label it to say secondary. However, bear in mind that when you're drawing this symbol, it is drawn horizontally and you label your primary to your left and your secondary to your right. But if you're drawing this in a circuit diagram, and let us say we do it vertically, your supply lines, and this is a transformer on this side. Right? This would be your primary, and this would be your secondary. So you see you have your primary on your left, and there your secondary on your right. However, if you draw the same transformer on this side, let me get rid of this. This would be your primary, And this would be a secondary. So when you join your transformer into a circuit, bear in mind that your primary side would be the one that is connected to your supply, regardless of how you join it, whether horizontally or vertically. Then you look at the construct. The primary side, yes, is on your left-hand side, and your secondary is on your right-hand side, and it says out, and it says in. So your primary is really your input, and your secondary is your output. Then it has lines of force. These lines of force cannot be seen with your naked eyes, but for joint references, we use this to show that there is a magnetic, or there are a number of magnetic lines of force that are being created, and they are transferred from one coil to another. And this represents your magnetic core. Principles of operation. How does a transformer operate? Can it operate just by throwing it in the air and it falls to the ground? No. A transformer operates by a changing or an alternating voltage is applied to one coil, and I said winding as well, which is called the primary coil, which creates a time-varying magnetic flux. Time-varying means that it requires time, and it is changing, so it might go up or down, in one core, which induces a voltage into the second coil. And bear in mind, the second coil is the secondary coil. Transformers come in range of sizes from very small, like maybe a little bit of size of your fingernail, to huge transformers, very, very huge transformers. And may I just say, transformers, those things that you see on your light pole in your area, perfect example of transformers. From coupling hidden inside a stage microphone, think of how small a microphone is. Transformer may be in here. But all of these transformers operate on the same basic principle. That basic principle is called mutual inductance or inductive, right here. Have the same principles. The principles are called mutual inductance or, did I tell you before? All right, we get back to that. A transformer has no moving parts. That means you just put it down right here like anything on your table, and it doesn't have to move any at all, and it operates. And the energy is transferred from one coil to another by means of electromagnetic induction. So I said mutual inductance before, and that's one. So I was hoping that, my students would tell me that the other one is electromagnetic induction. The primary coil, and I said it before, is connected to the power supply. So let's go back here. This is my power supply, live, neutral. And let us just use live and neutral for now. The primary coil is connected to my power supply. So this transformer has a primary on its right and the secondary on its left. This transformer has its primary on its left, this one on its right. This is for the purpose of a diagram where the transformer is now being in operation. The primary coil is connected to the power supply, and it will give out a version of voltage that is either less than or greater than the voltage that it is connected to. And this is dependent on a number of things. One, the number of turns in the primary coil, the number of turns in the secondary coil, and the voltage that it is applied, it is connected to. So we are looking at four main things: the primary coil, the secondary coil, the primary voltage, and the secondary voltage. But bear in mind, it says the primary is connected to the power supply. So that voltage in the primary is called your primary voltage. And the transformer will give out a voltage, which is called the secondary voltage, which is going to be either greater than or less than the voltage that it was connected to. A transformer that gives out a lower voltage than the input is called a step-down transformer. At the beginning, I said students will write the lesson to say a transformer is a device that step up or step down voltage, full stop. Yes, they are correct to some extent, but bear in mind I said it also does that with current, and it does it at a constant frequency. A transformer that gives out a lower voltage than the input voltage is called a step-down transformer. A transformer that gives out a voltage higher than the input voltage is called a step-up transformer. Transformers by classification. How do we classify transformers? Transformers just don't come and you say a transformer is this, a transformer is that. How do we classify transformers? Transformers are classified using numerous applications and may be classified in many ways. One, by power level, from fraction of voltage ampere to thousands, even mega volt ampere. By the power level, by the application, the power supply, impedance matching, circuit isolation. By the frequency range, for example, in audio, in radio, you have a transformer that can change the frequency to how you hear sound on XYZ. Then, by cooling type, what method do they use to cool a transformer? Air, oil, water. By voltage class, a voltage can be from 110 volts, 50 volts to megavolts. The ratio of number of turns, and this is what we're going to be using today mainly, because we're going to be talking about the relationship between number of turns in the primary, number of turns in the secondary, the voltage that is applied to the transformer, and what voltage the transformer will give out. Isolation transformer, intended to transform from one voltage to the same voltage, meaning whatever voltage goes into the transformer, practically the same voltage you're getting out. Relationship between the number of turns in the primary, the number of turns in the secondary, the voltage in the primary, the voltage in the secondary, the current that flows in the primary, and the current that flows in the secondary. Now, if we look closely, we can look at it. It says if the voltage that is applied to the primary of a transformer is divided by the number of turns in that coil, or say windings, the result would be known as volts per turn. The volts per turn in the primary is the same as the volts per turn in the secondary. And thus we would have an equation looking like this. The ratio between the number of turns in the primary and the secondary turns is equal to the ratio between the primary voltage and the secondary voltage. So I put in bracket primary and secondary. So you could say it the other way around by saying the ratio between the number of secondary turns and the primary turns is equal to the ratio between the secondary voltage and the primary voltage. And of such, you would have these two equations. Vp over Vs is equal to Np over Ns. Or you could write Vs over Vp equals Ns over Np. And here we have what each means. Vp means volts in the primary. You want to say volts on the primary side. Vs is volts in the secondary. Np is the number of turns in the primary. And Ns, the number of turns in the secondary. Now when you have two equations, two formulas, two fractions equal in each other, we can do what is called cross multiplication. So let me bring you through that. So we have Np over Ns, right, is equal to Vp over Vs. So we're using one of them. We could use any one. It will come back to the same result. So when a fraction equals another fraction, we do what is called cross multiplication, right? So now I'd have this part multiplied by this part multiplied by this part. What do we have right here? We have Np, so this would give me Np multiplied by Vs is now equal to, you could say Ns multiplied by Vp, or you could say Vp multiplied by Ns. It matters not which one of them you put first. So I could have Ns multiplied by Vp. All right? And that would be your equation coming from what we have as fractions. Now, when we have it looking like this, from this, we could now derive a formula for any one of the four. So let's look. The following would be the formula for each what? VP, NS, NP, or VS. Any one of the four you want to find a formula for, you can come right here and do it. How do we do that? I always have a smart way of telling how to get it. If I want to find NP, I would remove what I don't want to find, which is VS. So what I would do is, let's say, rub out VS, and I would draw a line on the other side here. And what did I remove from here? I removed VS. So I will put VS right here. So if you look at the formulas, I would have NP is equal to NS multiplied by VP over VS. So you'd have a formula for each of them. So any three that is given, you can find a fourth by using any one of these formulas. So let's go into an example. An example reads, a transformer having 200 turns in the primary and 800 turns on the secondary is connected to 400 volts. Connected to 400 volts. Remember, the side that is connected to a supply is called the primary. So right away, students, this is your primary voltage. And is supplying a load. What part of the transformer gives out? What part of the transformer supplies? Is the secondary. Calculate the primary and secondary volts per turn. And remember back then I said the volts per turn for the primary is the same as the volts per turn for the secondary. So anything you get for the primary will be the same for your secondary. And also calculate your secondary voltage. So we set it out looking like that. 1. VP over NP, which is called volts per turn. But this volts per turn is for your primary. And it is the same as the volts per turn for your secondary. What's the voltage in the primary? The voltage in the primary was 400 volts. What's the number of turns in the primary? 2000. And that becomes 0.2 volts. So for each turn in the transformer, we would get 0.2 volts. Transfer this to your secondary, it would be the same, 0.2 volts. Now it says find your secondary voltage, or the voltage that supplies the load. And here's your equation. So let's go over here. Remember to set out the formula that is for your primary. And we said VP over VS, which is primary voltage divided by your secondary voltage, is equal to your primary number of turns divided by your secondary number of turns. What do we want to find? VS. Therefore, VS is equal to VP multiplied by NS over NP. Then we're going to now plug in the values of each of these. What's the value of VP? 400. What's the number of turns in the secondary? The number of turns in the secondary was 800. And if we go back, we could find what's the number of turns in the It says the number of turns in the primary is 2000 and the number of turns in the secondary is 800. So we put 2000 down here. Now by virtue of using your mathematics skills, we could cross off 1 0 here, 1 here, 1 0 there, 1 there, 1 0 here, 1 here. All right? Then we say 2 into 2 goes 1, 2 into 8 goes 4. And then we multiply across, and 4 times 40 is equal to 160 volts. And that would be your answer, student. And if you look, we have 160 volts. It also says you could use what is called your volt per turn. Using the volt per turn method, how many turns were there in the primary? 2,000. How many turns in the secondary? 800. Don't get them mixed up. Remember, you're working on your secondary side, so you have to use the secondary number of turns. All right? When a transformer is given, when a transformer steps down voltage, it steps up current. And vice versa, meaning if it steps up voltage, it steps down current. Therefore, the ratio expression for voltage is the inverse for current. And you will get this equation. Vp over Vs, which is voltage on the primary, divided by the voltage on the secondary, is equal to the current in the secondary divided by the current in your primary. Also, remember in the first place we have Vs over Vp over Vs is equal to Np over Ns. So I could also write Np over Ns equals Is over Ip. And then everybody equals each other, given ratio. So this is your voltage ratio, this is your turns ratio, and this is your current ratio. A transformer given in ratio term will tell if the transformer is a step up or a step down transformer. Remember, we're talking about voltage mainly. When a transformer is given in the ratio terms, it indicates the voltage and the turns ratio. The inverse of this is your current ratio, but we mainly focus or use the turns ratio and your voltage ratio. For example, a 4-to-1 transformer or a 2-to-1 transformer, and I could say a 3-to-2 transformer or a 5-to-2 transformer, is a step-down transformer because what? The primary comes first. Whilst a 1-to-3 or a 1-to-5 or a 1-to-4 would be a step transformer. This tells you that the number of voltage on your primary is 4 times bigger than the number of turns on your secondary. This tells you that the number of turns on your primary is 2 times the number of turns on your secondary. And this will tell you that the number of turns on your primary or the number of turns on your secondary is 5 times the number of turns on your primary. Example, a 4-to-1 transformer with 300 turns in the primary windings is connected to 200 volts. Look again, students. Connected to 200 volts. Connected to. What side of the transformer is connected to a supply? The primary. So this is your primary voltage. And supplies and delivers a current of 2 amp. Delivers mean it is giving out a current of 2 amp to a resistive load. Calculate the secondary voltage, calculate the number of turns in the secondary, and calculate the current flow in the primary windings. So we are asked to calculate 3 things. But you're given a ratio. You're given the number of turns in the primary, and you're given the primary voltage, and you're given the current flowing in the secondary coil. So here we go with working out. Vp over Vs, which is your turns ratio. Your turns ratio that was given, sorry, your voltage ratio. Your voltage ratio that was given was 4-to-1. 4-to-1, as you would write it, is written as 4-to-1. But this written in fractional form is 4/1. So this is the ratio set out, but this is your fractional set out, which is the same thing. So Vp over Vs is equal to 4/1. What this is saying to you again is that your primary voltage is 4 times bigger than your secondary voltage, right? So to find your secondary voltage, all you have to do is to divide your primary by 4. Why? Because it said it is 4 times bigger. So we move on. Therefore, Vs is Vp over 4, which is voltage on the primary divided by 4. 200 divided by 4 gives me 50 volts. So the transformer is connected to 200 volts. It is giving out 50 volts. NP over NS. What is this again? Your turns ratio. Turns ratio 4 over 1. It means that your primary turns are 4 times the number of your secondary turns. And you go ahead and do the same principle. NP divided by 4. 300 turns on your primary. Divided by 4 gives me 75. It says find the current in your second and your primary turns. IS over IP. You see the inverse right here now? This is the inverse that we're talking about. The inverse for your voltage is your current. So this is saying that your secondary current is 4 times bigger, or 4 times greater, or 4 times the amount of current that is flowing in your primary. So what do? Divide 2 by 0.5. By 4 gives you 0.5. And you have an exercise right here. The exercise, determine the unknown. From this set out, you could write a statement. Or from a statement, you could actually put your data form. This could be written in words to say, a transformer with 1500 turns in the primary is connected to 240 volts with a secondary turns of 500. The current flowing through the primary coil is 1.5 amp. Determine your secondary volts and also your secondary current. So we move to doing the calculation, students. We're going to set out our equation again according to how it was given. I am hoping that somebody home is going to work this fast enough, faster than how I'm going to be doing it. So VP over VS is equal to NP over NS is equal to IS over IP. All right, so we're going to plug in our values. What's NP? NP is 1500, so I could write 1500 right here. What is VP? 240, so I could write 240 right here. What is NS? 500, so I could write 500 right here. What is VS? Unknown, so I'd leave VS. What is IP? 1.5, so I could put 1.5 right here. Now, which of the fraction is completed? This one is completed. So I would now go 0, 0, 0, 0. And we say 5 into 5 goes 1, 5 into 15 goes 3. So here I now have a ratio of, what's the ratio? 3 to 1. So what do I do with this now? I must get this fraction down to a fraction of 3 over 1. Good? So for me to find VS, I would simply say VS is equal to 240 divided by 3. 240 divided by 3 gives me, very good, I see that. 240 divided by 3 gives me 80 volts. All right? And then I move over here and I will do the same thing. This one should be 3 over 1 again. That means I should have a fraction that when I divide by 3, I get 1.5. Because IP over IS is equal to 3 over 1. See that? But I already have IS. So what do I do to find IP? I said IP is equal to 3 times IS. Isn't that right? And 3 times 1.5 gives me, don't say 45, but 4.5 amp. Very good. So we can look at what we have here. All right. So we're moving on. Energy losses and efficiency. Energy losses and efficiency. Because current is flowing, we're going to be losing some form of energy. Because current is flowing, we lose energy through what is called heat loss. All right. An ideal transformer means it is real, theoretically it is real, but practically, you might have some form of differences. An ideal transformer can be considered 100% efficient, 100% efficient. But in practice, energy is dissipated due to both the resistance of the windings known as copper loss and the magnetic effect of primary attributable to the core known as iron loss. So the two main losses in transformer, they are called copper loss and iron loss. Transformers are in general highly efficient. Why? Because this is due to them not having moving parts. Remember earlier I said that transformer has no moving parts. The transformer losses arise from winding resistance, which is the current flowing through the coil, and the resistance of the coil, square, the eddy current loss, hysteresis loss, mechanical loss. We will read them. You will get them so you can read them. In addition to magnetic-striction loss, the alternating magnetic field causes fluctuation, and the fluctuation will cause some form of vibration and so forth. Stray loss. Not all magnetic field produced by the primary is intercepted by the secondary. That means you have something along the side might be taken away some. All right. What is efficiency? How do you define the word efficiency? The efficiency of a transformer is the ratio between the input and the output. The efficiency of a transformer is the ratio between the output and the input. It means that whatever you get out of the transformer compared to whatever was given into the transformer, that is called the efficiency. A transformer can be considered 100% efficient, meaning it is ideal, as I said before, ideal theoretically. But in practice, we have losses. Because it has no moving parts. But its efficiency is affected by two main losses. And I did say them before. What are they? They are called core loss and copper loss. And if students should write copper loss first and core loss after, no problem. The core loss is due to the hysteresis and the eddy current, while the copper loss is the loss due to the primary and secondary windings. Remember, the windings are made of wires, conductors. And because they are made of conductors, current flow through, resistance, heat loss, I square R loss, and that is power loss. But they have two sides, a primary and the secondary. So you don't isolate them. The primary loss is added to your secondary loss to give you your total I square R loss. The efficiency of a transformer can be determined by the given formula. So bear in mind, students, in electrical, we have a lot of formulas. You have to practice your formulas. You have to practice your math. You have to understand how to use your calculators. All right. Efficiency is equal to your power out divided by your power in, and then you multiply by 100, and it is expressed in percentage. So if you are calculating something and you calculate and you get a figure, don't just write 96.7. Efficiency is expressed in percentage, so you have to put your percentage. What's the meaning of these? PO. What is PO? Output power, or you say power out. What is PI? Input power, or you say power in. And this is efficiency. From the formula for apparent power, VI, which means V multiplied by I. Power in would be primary voltage, of course, not secondary, not just any voltage, but your primary voltage multiplied by your primary current, and your power out would be your secondary voltage multiplied by your secondary current. It says if a transformer is considered ideal, then the input power is the same as your output power. So anything that you get in is the same thing that you get out. But bear in mind, again, students, we say that's ideal theoretically. Practically, you will not have that. So therefore, what's for power in? VP multiplied by IP would equal to VS multiplied by IS. Considering the losses, what were the losses we talked about? We talked about your I square R loss, which is called your copper loss, or your core loss, which is called your iron loss. considering these two losses, the output power is less than your input power, of course, because you put some stuff in and you lose some away along the way, you must get something less in practice, all right? So we look at the formula. Power in would equal to your power out minus your losses, all right? And what are your losses? Iron loss plus your copper loss. I use your chemical formula or symbol, Fe for iron and Cu for copper, and your efficiency. So I remove now power out up here. And what is your formula for power out? Here is it, power in minus losses. So I put power in minus losses, all right? By coming here, when you have a fraction looking like this, you would have power in minus losses over power in. You could split this in two to say power in over power in minus losses over power in. All right, I'm going to be leaving it right there for today, and then we get back at another date. Until next time, I am Fitzroy Hibbert.